Hello, this is Jennifer Martinez, and today I'm going to be lecturing on the matrix of a linear transformation. In this section, we are going to show that every linear transformation can be written as the matrix transformation. And we are going to find that matrix using the identity matrix. So let's review the identity matrix. If you remember, an identity matrix is a square matrix with ones along the diagonal and zeros elsewhere. It's denoted by I, or sometimes I sub n, for a n by n matrix. Note, if I times some vector x is always going to be equal x, and in times some vector n is always going to be equal n for all x and xn. To see this, let's let example in R2. So x would be x1, comma x2. So I2x would be the matrix 1, 0, 0, 1 times x1, x2, which would indeed be just x1, x2. If you take the first row times this column, you get x1, and the second row times this column, you get x2. So you can see that that does work. We are going to let I sub j be the jth column matrix of the identity matrix in Rn. So In, your identity matrix, can be written as E1, E2, all the columns in terms of E. This is going to be useful in this section as well. Let me do an example of that. So what would I3 be written as? It would be written as E1, E2, E3. Where E1 is the first column of that identity, E2 is the second column, and E3 the third. We're going to use these E's to find formulas, to find the matrices for our transformation. So let's do that using example 1. It's our next example. So I2, we know, is 1, 0, 0, 1. E1 is going to be the 1, 0. E2 is going to be the 0, 1. Suppose T is a linear transformation from R2 to R3. We have, because E1 is in R2 and this is in R3. With no additional information, find a formula for that image. So we're going to find that formula. We're actually going to find the A. So what I'm going to do is I'm going to let T, right, go from R2 to R3, and I'm going to choose an arbitrary X in R2. So we know X can be written as some X1 and X2. We're going to write this in terms of the E's. So what I'm going to do is I'm going to split this up, X1 and 0 plus 0, X2. into two separate vectors where x1 is my first identity times my first identity and x2 is times my second identity. So now you can see we just have x1 times e1. Whoops, x1 is a constant. x1 times e1 plus x2 times e2. x1 and x2 are just entries, they're not vectors. So now if I look at t of x, what is that going to be? That's going to be t of x1 e1 plus x2 e2. Since that's just another way of writing x. Oh, but t we know is linear. So we can And x1 and x2 are constants, so we can just take out, well, we can do two things. We can split it up and take it out. So I'm going to do both of those in one step. Now, these are actually vectors, and these are vectors given. So that is actually going to now be x1 times t of e1, which they give you right here, and x2 times that e2 vector, negative 3, 8, and 0. Okay, let's make that into one matrix. So we know that's going to be equal to, if I look at that and just bring this x1, bring this x2 in, that would be 5x1. I feel like that's way too small. 5x1 minus 3x2. That's better. Negative 7x1 plus 8x2. And lastly, 2x1. Oh, just 2x1. So now I can actually rewrite this. I can actually rewrite this as just with the coefficients 5, negative 3, and negative 7, 8, 2, 0, with a x1, x2. This does make sense, because again, this is a 3 by 2. This is a 2 by 1. So the result is a 3 by 1. And if you multiply these out, you can see that this would be 5x1 minus 3x2. This next second line would be negative 7x1 plus 8x2. And the last line, the last entry is just 2x1. If you notice, here's a matrix times x. So that A, we found the A, the transformation that's going to make that happen is right there. In general. So notice, by the way, notice that this was just t of E1 and this was t of E2. If we go back up just a, right, t of E1 and t of E2, it's just those two columns. So in general, we have this really nice theorem. It says, let t be a transformation from Rn to Rm, linear. Then there's going to exist a unique transformation A, such that t of x equals ax for all x and xn. In fact, the actual matrix that you find, A is an n by n matrix whose jth column is the vector t of ij, where e of j is the jth column of the identity of the matrix Rn, and there it is. That is going to be the A. The A is just all the transformations at each identity column. Or a better way of saying it, the transformation of each column of the identity matrix, In. On this one, I'm actually going to do the proof because the proof is example 1. So in general, let's go ahead and do that, the proof. So we're going to let T go from Rn to Rm, be a linear transformation, and suppose x, the vector x is an Rn. So x from above should be In times x. Again, this is easy to see because this is just E1, E2, all the way to En. And this will be x1, x2, all the way to xn. And this you can easily multiply because this is 1 by n, this is n by 1, so it's going to be a 1 by 1 matrix, or a 1 by 1 quantity, and it's going to be the first, these are vectors, these are entries, so it's going to be x1 times e1 plus x2 times e2 xn, oops, I have those in the wrong place, en. Okay, it makes sense, and you don't need to have a matrix there because that's just a 1 by 1. Again, this is a 1 by n, and this is a n by 1. So you end up with a 1 by 1, and you don't need to put that in a matrix because it's a 1 by 1. Okay, and so now we're going to look at T of x. We're trying to find that formula. So T of x, we know is T of this. And we know that it's linear, so we can split these up. T of E2. And we know that we can change this. We saw above that this is really just T of E1, T of E2, dot, 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 T of En, times the same as above. This is a 1 by n, and this is an n by 1. So the answer should just be a 1 by 1, which is what this is right there. And what is that equal to? It's equal to a, that's going to be our vector a, times some x. So we just found the a. We just found that matrix. Where a is T of E1, T of E2, dot, 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 T of En. That is our matrix transformation. So we proved it. There exists a matrix A such that T of x equals AX for all x and xn. By the way, it is unique. To prove that it is unique, you can look at an exercise in the book. But if you did try another one, a B, it would end up being the same answer. So it is unique. So this shows that every linear transformation can be written as a matrix transformation in the form T of x equals AX. There exists a unique mapping. So that means that it can be written always in that form, and this is that matrix. So let's try an example. Let's look at example 2. Example 2 is an example of a dilation transformation. It says find the standard matrix A for a dilation transformation of T of x equals 3x for x and some R2. So was a dilation matrix of 3x equal? So if you take this U right here, you multiply it by 3, it's going to dilate it, or it's going to, right, 3 times U. It's going to make it 3 times as long. So we know to find the matrix, we're just going to look at our E's. We know E1 is 1, 0, and E2 is 0, 1. So I'm going to start with E1. T of E1 is 3 times E1, which is 3 times 1, 0. Multiply that by 3. This is the first column of our matrix. And if I look at T of E2, I did it down below here, T of E2, again, using this formula, is 3 of E2. E2 we know is 0, 1, and 3 times it is just 0, 3. So our matrix is E1 is the first column, E2 is the second one. Again, this is equal to T of E1, T of E2. You could check it. Our U here looks like maybe negative 1, 1. So if I take A, my matrix, times negative 1, 1, I should get 3 times it, and I do. Right? I get negative 3, 3.